Hello, students. Taking a look at some 8-3 questions, starting off with 6B. Let's take a look. Question from the student was, how to make a rule when there's an X, Y for the input? So I think it's just remember, it doesn't matter what your input is. It's just what you're doing with the input. So this is what it is here in 8.3B. Let me go back and see if they got a similar one for A. I mean, kind of. This one is explicitly state the actual rule, whereas ours is more of kind of create the rule, if you will. So just to give a little bit of a reminder, when you are creating a rule, look for a pattern. Try to find, there's so many different ways I can get from 3 to 7, right? It could be that 3 plus 4 is equal to 7. That's one way. It could be that that's like 3 times 1. It could be 3 times 2. Okay, well, 3 times 2 is 6, then plus 1. There we go. I mean, that could be that. It could be 3 times 3, which is 9, but then I take away 2. So all of these are ways to get from 3 to 7. So what you want to do is try one and see if you can kind of make it work for all of these inputs, not just 3. Now, you could create an actual, like taking these ordered pairs and just kind of create your own. So think about if you had something that said, okay, so if I have a coordinate x, y, what I'm doing with it is I'm doing x plus y. Okay, so just for a second, think about that. Okay, and then if I throw in a little white space over here, then it's like, well, where would that go? What would that map to? And so 0, 3 would map to 0 plus 3. So that would map to 3. Okay. Then 3, 5. Well, that's going to map to 3 plus 5. So that's going to map to 8. 2, 9 would map to 2 plus 9, which would get us to 11. And 4, 5 is going to map to 4 plus 5, which gets us to 9. So that's how it would work. So if you saw this, you could start saying, hey, it looks kind of like I'm adding the digits together. So you're creating the rule. Okay. Well, now if you go back, that's not what's happening here, but I want you to think it can be somewhat close. A lot of times when you see things like 0, 3, and it gets me to 3, well, maybe then there is something where I'm adding on that second digit. I don't know what's happening first, but I know I'm going to add that second digit. So if you can think like that, maybe then you can come over here and say, well, what would it look like if I took away 3 just to help me see better what's happening with that first component? So if you take away 3, you'd have 0, you'd have 11. Took away 3 because 3 was that last digit. Next one, I'll take away 5. I should say it that way. So take away 5 from 14, and that's going to be 9. Take away 9 from 13, that's going to be 4. And take away 5 from 21 is going to be 16. So if you take a look at these numbers, maybe something trips a little bit, because now you look at how do I get from 0 to 0, from 3 to 9, from 2 to 4, and from 4 to 16. And I hope that gives you a push to kind of say, okay, I can see how that relationship works between those components. Okay. Let's see here, 14C was the next question. Let me draw down here. Next page. Okay. 14C. Okay, it's this one at the top. And it says, consider the function f of x equals the opposite of x plus b, where b is a constant. Find the following. Find all inputs for which the final output is this. F of x equals x. All right, throw a little white space in here. I know. If you're looking at the clock on my screen, it says 1:39 a.m. It's been a day, but I didn't want to leave you hanging anymore. So sorry it took me this long to get to it. F of x equals, okay, so think about it. What you're going to do is, first thing you're going to do is f of x, which you know is the opposite of x plus b. You're going to take that and you're going to put it in where you see the f of x, because that's what it's equal to, and you're going to take f of that. Okay, so that now means I'm doing f of opposite of x plus b. Okay, but f of x, and this is where sometimes it's helpful to say, hey, what if this wasn't f of x? What if it was f of cloud? Well, then there'd just be a cloud over here. So in your case, what's in the cloud is this thing. And that is going to go inside the function. It's going to equal the opposite of cloud, which is the opposite of x plus b. And then it says over here, plus b. Okay, there's your cloud. And now simplify a little bit. So the opposite, I have an opposite out here. I have an opposite of x minus b. We've seen that before, where we can, in a sense, distribute the opposites. Let's see here. Now take a look. I have the almost like a negative b plus b. So those are going to eliminate. Leaves me with the opposite of x. And the opposite of x is just x. So find all inputs for which the final output is x. Hey, I got to tell you something. The final output is always x. So maybe you could say something about this. Which inputs will work? Is it just a few of them? Is it one specific one? Or maybe, hey, all of them work. Okay, let's see here. 16, although I found the answer to this question. Hey, is there a faster way to solve 16? Oh, okay, yeah. There is a connection between A and B. So for these, I have a feeling that for part A, if you know the output is something squared, that you would take the square root of it. Okay. And it does say up here, the nth term of a sequence to a natural number. Okay. Yeah. Hmm. Hmm. I don't really like that wording. I think that wording is pretty crappy because it says T of n is a function that assigns the nth term of a sequence to n. So it tells you the output should be n. And then part A says it equals n squared. So we'll just pretend that's not there. Something, to something that's in the natural numbers. Okay. So when you look at this, though, as you're taking a peek at this, what you really want to be thinking is, okay, wait a minute here. So if I know I have like the number 5, like the number 5 is my input, then the output I get is 5 squared because that's the rule. That's the function it tells me. Okay, so that means I have 25. Oops, that got a little weird. Sorry about that. So I have 25. So if they gave me 25, how do I get back here? And that's where it'd say, oh, I just take the principal square root. Okay, square root of 25 is 5. So that's why you could go through here and you could just kind of take the square root and see if it works. So the square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. Square root of 10, sorry, that one fails. And let's see here, square root of 900 is 30. Okay. Now, it may not seem like there's a connection between A and B, but I want you to see in part B, they say T of n is equal to n times n plus 1. And the reason I do this is I want you to notice this is n squared plus n when I distribute. Okay. And again, if you had numbers like n squared and you had a number like n, the n squared, as you get larger and larger values, is actually going to dominate. So if you had the number 100, right, and you put that in for n, what is t of 100? Well, that's just 100 squared plus 100. But 100 squared turns out to be 10,000. So at the end of the day, your final result is I mean, if you were estimating, you could ignore the n, right? Just deal with the n squared because that's the thing that's going to take the biggest chunk. So when I do problems like this, if you're looking for an efficient way, I'm going to estimate quickly by ignoring the plus n and focusing on what I believe will be kind of the leading chunk. That makes it similar to the problem we just did because we just did one that was an n squared. So what I would do down here is I'd actually take a few numbers. You could also plug some numbers in, just kind of see the pattern. So let's say, what's t of 3? I don't know, maybe that's too small. What is t of 2? Okay, t of 2. So t of 2 would be 2 times 2 plus 1. That's what it says right here. I'm just using the rule. And 2 times 2 plus 1 is 2 times 3, which is 6. Okay. Now, since I told you my way is estimating is ignoring this piece and just taking the square root. The square root is 6. I'm going to come up with some crazy decimal. But I do know one thing. I know the square root of 6 is bigger than the square root of 4. I can guarantee you that. And the square root of 6 is also less than the square root of 9, right? It has to be. So then when you look at it, all you're really looking at here is that we know that the square root of 6 very quickly is between 2 and 3. And since the square root of 6 is between 2 and 3, you can kind of get a pretty good idea that your number has got to be between the 2 and the 3. Okay? That's where yours kind of has to be. So let's try it here, okay? So when you take the square root, you're going to pick kind of the whole number above and below it, and that'll be kind of the way you help yourself out. So let's take the square root of, what do I want to do? The square root of 12, okay? Okay, so when I do the square root of 12, right? Square root of 12 is approximately 3.46. What I do is I can kind of say, hey, wait a minute, why don't I go down and up? It has to be between two whole numbers. So I'm going to say it's between 3 and 4. And so what you do is you can kind of check 3 times 4 is the same as 3 times and 3 plus 1. And so you can kind of say, oh, yeah, that actually does fit perfectly because it turns out 12 is the same as 3 times 4. And that is what I would be putting in. Okay. What else would that look like? Let's say we tried another one, right? If you try the one with the 2550, 2550, and I raise to the 0.5. Okay, so 2550, if I estimate it by taking the square root, I get about 50.49. So to me, that's like, hey, that's like 50 and 51 is what it's between. But the formula says you're always going to pick one number and the number 1 above it. So I'm going to check this. What is 50 times 51? And if it works out perfectly, then it was in the domain, or sorry, in the range. If it doesn't work out perfectly, then I'm sorry, it wasn't. Cool. Cool, cool, cool. All right, let's see here. Oh, let me clear my drawings. All right, number 20, 21, and 23. Okay, let's take a look. Number 20, not on this page. Next page. Number 20. Find the total number of matchsticks in the 4th figure. All right. So let's see here. Hmm. That kind of looks like a real pain to figure out. What a horrible nightmare. However, look for a pattern. I mean, really, wouldn't it be nice if you had these last two little pieces? Like you had one here and you had one there? To me, that seems like it'd be easier, right? So let's just pretend we did. Here we go. So if we did have what we actually have here, then I would have 2, 2, and 2 going vertically, right? So 2 plus 2 plus 2, that's my vertical pieces. And then horizontal, 2 plus 2 plus 2, which I guess, I mean, I could write as plus 2 plus 2 plus 2, right? Now just remember, I added 2 blue toothpicks in here just to kind of see the shape. So make sure you take away those 2 at the end. Okay. Yeah, I think I'm gonna try to shorten this because what I can see is I see there's 2 in a row, and I do that 1, 2, 3, 4, 5, 6 times. So I really end up with 6 times 2, and then I take 2 away, and that gives me 10. And if you do the same thing here, now I have runs of 3. So I have 3, 6, 9, 12, and 3, 6, 9, 12. Well, 12 and 12 is 24, right? So what I have now is I have 12 times 2, and I still have to take away 2 because I did count those pieces down here. So just take away 2. So that's 24 minus 2, which gives me 22. Again, if these were filled in, it'd be really nice. So just remember, I'm going to do something that makes it look like they're filled in, but they're really not yet. So now I have 4, and I have 1, 2, 3, 4, 5. So that's 5 groups of 4. And then vertically, I have that again, 2, 3, 4, 5. 5 groups of 4. Well, 5 groups of 4 and 5 groups of 4 is 10 groups of 4. And there you go. So if you were doing the same thing before, even though it can count 12 times 2, you could also say 3, 6, 9. So that's 3 groups of 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 8 groups of 3. So we have 8 groups of 3, 6 groups of 2, 8 groups of 3, 10 groups of 4. You can see where this is going. It's going to go to the 5 by 5 next. Okay. But maybe that helps. We got to break it down. If all you're doing is counting the number, sometimes you miss kind of how we came up with that number. So try that because I think that should get you all the way there. Let's see here. What else could you do? If you were just using the number, though, I guess I should say if you're just using the number, it is possible to create sequences. There's no guarantee that they'll continue because we're using inductive reasoning with that. But if we did create and we had like 10 and then 22 and the next one would be 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is 4 is 40, so 38. Okay. You can look at what are known as the comment or the differences, or what's known as first differences. So if I subtract 22 minus 10 gives me 12. 38 minus 22 gives me 16. Okay. Now, if you went and found the next one, again, this was a 3 by, this was a 4 by, this is a 3 by, this is a 5 by. So if I went up one more and I had a 6, right? Yeah, maybe that 6 have 6 by 6. Okay, so that's going to go up to be 58. And then here would be 20. Now, the reason why sometimes I'll do this is what you can see is if that's great, but then come down here and what do you notice? This one's going up by 4 each time. So what that means, the number 22 is really the sum of the 10 and the 12. Okay. Yeah, I think that's probably good. But I mean, if you wanted to see it, so then what you could do is you would start with 10 and then you just kind of add your way down and you'll get to the different terms. So the first term would be 10. The next term would be 10 plus 12. Yeah, because I think it's adding 12. Yeah. And then the next one is 10 plus 12 plus 16, then 10 plus 12 plus 16 plus 20, and off you go. So you've got this sequence over here that is like the sum of an arithmetic sequence. Now remember the sum of an arithmetic sequence back in 105, the sum was equal to the first plus the last, excuse me, multiplied by the common difference, and divided by 2. So no, if we were, let me go back and just remind, because I also am dealing with students who may not have taken the class, uh, like some of you did. If you're adding up an arithmetic sequence like this, 1, 2, 3, 4, 5, you can add them up by saying, I have this many. So 1 plus 5 is 6. 4 plus 2 is 6. And then in a sense, 3 plus 3 is 6, but really half of it. So what you do is you take the sum of A and B and you take half of it. And then you figure out that you have n terms. So you'd have like 5 of these half groups, and that would be like finding the average and going from there. So this is what you would actually be kind of doing. So you could do that technique here and say, I'd like to find the 20th term. Well, the 20th term means you would go, here's the first term. We always know that's 10. And then that means there's 19 more terms. And so you can create that, find the first term, which would be 12, and find the 19th term, dot, 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 dot. You're going to plug that in here for a sub n. You wanted so many terms, put in the number of terms, divide by 2, and you can find the sum of that. And that sum actually gets you back to those other numbers, because that's really what they are if you look at it. So that's a second approach you could use. Totally up to you. Okay, there's 20. Let's see here. 21. Okay, similar to 20 goes 2, then 5, then 9. So it goes up 3, then 4, then 5. Yeah, yeah. Hmm. I mean, this one's pretty nice, because if you look at it, it is kind of adding some pieces as you go, right? Here's the first term, and it's actually the first term sitting right here. So what you get, the difference is what you added. So I added 3, and that's the second term. I added 4, and that's the third term. Here you can think of kind of adding 2, and that's the first term. So whatever term you have, like 1, 2, 3, 4, 5, if it's the fifth term, then you got to think it's always going to be one bigger, which means I'll be adding 6. Okay, that's how you can figure out how much is in each term, because we'll just kind of have that sum as well. It's 2 plus 3 plus 4 plus 5. So the sum is 2 plus 3 plus 4 plus 5 plus dot, 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 dot. And for however many terms we want. So let's say you want n terms. So this right here, 4 terms would end with a 5. So n terms would end with an n plus 1. All right. So I add them forwards and I can add them backwards. This becomes n plus 1 plus plus n plus plus 2. So what I end up with is when I add them, I get n plus 3 plus n plus 3 plus plus n plus 3. And I know how many of those I have because I've done this to make sure that I have n terms. And so it's this thing, when I add them all together, find out how many there are. Yeah, multiplied by n, because this is the nth term. Yeah. And that's what it says. It says find a formula for a sub n in terms of n. So once you find the sum of this, that will be your a sub n. Okay. Very cool. Let's check and see. The last one, I think. Maybe it says 23D, 23D. So here's D, this is 23, right? 23D, and it says, is this a function? So you can check. A function means every input has exactly one output. You could also check that by using, so like a visual definition. So if you watch, you can grab this tool and drag it. And wherever you set it, like it better be touching exactly one output. Okay. So if it's ever not touching one output, you know that it fails as a function. So down here in part E, I can see, and that's again what this is kind of helping to show me, is I can see that it intersects the line twice, which means I have two outputs for one input of the number 2. And so right off the bat, then that would be, yeah, that's not going to be a function. If you remember from high school, this piece we're kind of doing the up and down piece is known as the vertical line test. That's a visual way of seeing whether or not your function, whether or not your relationship is actually a function, I should say. All right. And let's see here. Lastly, Math Connection 14. We might have done something like this one in class. Yeah, this is the input that takes 2 in and gives it 1 out. So again, if you're dealing with students in your class, try to tie it back to some of the concepts you've already learned. Look at the operation here, right? It's just addition. So think about addition. What does addition require? Addition requires 2 values. What does addition output? It adds them together and gives you the sum, which is a single number. And so a student could say, oh, this doesn't represent a function, but you have to think, for each input, do I have exactly one output? Now, the input could be 2 things at the same time. They're coming in together, but them coming in together represents a single input. The input just happens to be something for X and something for Y, or what's known as an ordered pair. So that's the kind of the big idea. Yeah. All right. Hopefully that gets you going in the right direction. I got my fingers crossed for you. If not, let me know. I'll try to put something else out there, or I can meet up with you on Zoom or on campus. All right, it is 2:02 a.m., so I think I'm going to call it a night. I hope you all have a good evening and best wishes. Off you go.